Welcome everyone to the second unit. We are looking into the derivatives now. We are going to develop some equations to help us with more general forms of derivatives and even look at what a derivative really is. So in the last unit we looked at the slope of the tangent to the curve, any type of curve, and we used this definition for specific points. So specific x values that we looked at last unit. But now we're going to look at just general forms, general derivatives for any points on the curve. Example 1. Determine the slope of the tangent to the curve y equals x squared at any value of x on the curve. So not just a single specific point, but any point. Let's start with the same definition. So slope of the tangent, we start by saying limit of h approaching 0. My function, when I plug in x plus h squared minus my function of x is just x squared over h. This, if I expand using the perfect square, so x squared plus 2xh plus h squared minus x squared over h. Cancel my x squares, and I'm just left with some terms that all have h's in them, right? So I'm gonna cancel one h from each of them. And that's only possible when you have h in each of the terms that are left. Just speeding through a little bit just so that we can get to our general formula. So my h on the bottom is gone. 2x plus h is all I'm left with. And let me plug in 0. You have 2x. So my general formula for the slope of the tangent for any points on y equals x squared is 2x. So now I can take this and start plugging in different points. I don't have to do this calculation over and over again. Very convenient. So find the slope of the tangent when x is 2. So for example, if I had my curve that looks like this when x is 2, what's the slope? Well, I can just simply plug it into my formula that I found. So 2 times 2, which gives you 4. So the slope of the tangent when x is 2, this tangent line is, slope is 4. What about when x is negative 3? Well, let's plug it in. 2 times negative 3 is negative 6. So if I find negative 3 somewhere around here, let's say, and if I drew a tangent line for my point negative 3, what's the slope of this tangent line? Well, plug it into my equation and it's negative 6. So here the equation for the slope of the tangent to the curve y equals x squared is 2x. And I can plug it into this equation to find any slope of the tangent for any different point on this curve. So definition here. The derivative of any function f of x is the equation for the slope of the tangent at any point. Okay, that's important. So the derivative is the slope of the tangent for any point of x. Not just a specific point, but just any point of x. That's why you have this formula or equation. Some ways to write or symbolize derivatives. We've got a couple different ways. F with an apostrophe x, we read it f prime of x. You can write dy by dx, almost like a fraction there, I guess. So we read it dy by dx. This just means it's like change of y, like delta y, change of y, over change of x, like delta x. There's another name for the specific notation. It's called the Leibniz notation. He was one of the mathematicians that contributed to the development of calculus. And another method, we can write simply y prime. So just different ways of reading or writing derivatives. So the derivative of f of x, any function, is f prime of x. And we still use the same equation here. We call that the first principles definition. So now it has a name. So the first principle definition of the derivative, this is kind of like the basics of how do you find the derivative for any function. You always kind of come back to this first principle to figure out derivatives for new functions. Another term you might want to know is differentiate. So we already see it here, but when I ask you to differentiate a function, that just means find the derivative. That's all it means. So you'll see just different words that we use around derivatives. So note, if the limit does not exist at a certain point x, the limit is not differentiable at that point. Because our derivatives, it's still tied to limits, right? So if you don't have a limit at that point, you can't differentiate it. There are some other instances, examples here, where you cannot have a derivative at a certain point. So first one is when you have something called a cusp. This is the absolute value function. When you have a sharp corner in a function, you call it a cusp. You can't differentiate at that corner because if you think about it, you have just a sudden change in your tangent. So tangent coming from the left side has a slope that looks like this, but a tangent, once you turn that corner on the other side, suddenly looks like this. So you don't have the same value. You're suddenly turning a corner, so can't differentiate or find the derivative at that point. When your tangent line is vertical, so when you have a vertical tangent, you can't differentiate as well. The last one is when you have a discontinuity at that point. So for example, this is an asymptote. If you ask me what's the derivative or the derivative at the certain point, well, I don't know. You can't tell. It doesn't exist because there's a discontinuity right there.